We present FoodSkin, a technique for adding interactive elements to foods by implementing edible gold leaf circuits on the food surface. Our technique enables the integration of dry foods into an electronic circuit and provides displaying and sensing functionalities. FoodSkin enables enhancing the eating experience, such as presenting electrical taste sensations at multiple arbitrary points in foods that are tasted entirely or primarily in the oral cavity. The resistive heating element can be integrated into the food by creating a cone-shaped trace, allowing the chocolate on the element to melt. We create a trace on the inner surface of a fondant chocolate. Applying an electric current to the trace heats it, keeping the chocolate inside melted. Resistive heating elements can also be utilized for the olfactory enhancer. Warming the surface of the almond cakes causes the aromatic compounds to evaporate more easily, thus emphasizing the scent. This example shows interactive chocolate candy using capacitive sensing element that emits a sound from an external speaker upon consumption. The resistive sensing element enables monitoring of users' eating behaviors. When the user bites into the food, a portion of the trace is damaged, resulting in an increase in the resistance used to detect a bite. The fabrication workflow starts with designing the gold leaf traces by using the design support system. The user specifies the area where the interactive element is to be applied to a selected 3D model, and the system previews the preset traces of interactive elements to fit that area. The user can edit traces using the 2D editor. During this process, the system displays a warning message when the user makes edits that cause design errors. The user positions the wafer paper over the gold leaf and then covers both with wax-coated paper. The user gently rubs the top surface of the wax-coated paper, resulting in the adherence of the gold leaf and wafer paper. The user places 2 layers of wax-coated paper on top of each other and secure them to the cutting bed of the laser cutter. Laser cutting process is performed on the wax-coated paper. The user inserts the gold leaf between the wax-coated paper and performs the cutting process. This process reduces the adhesion between the wafer paper and the wax-coated paper and prevents damage to the conductive trace during removal from the cutting bed. The user applies a thin adhesive layer and carefully places the gold leaf trace on the food surface. We conducted a technical evaluation to assess its durability, adaptability to foods with various surface characteristics using linear gold leaf traces on 3 different thicknesses of wafer paper. We confirmed that conductive traces achieved good adhesion on various properties of the food surface. Regarding conductivity, durability to tensile and unevenness was higher for traces made with thicker wafer paper. We also confirmed that the measured resistance of the traces was in an acceptable range for our applications. We investigated how the taste and texture of the food differed when gold leaf traces using wafer paper of different thickness were adhered to the food compared with unprocessed foods. We confirmed that processed foods with thinner wafer paper tend to taste closer to the original than those with thicker wafer paper. Considering that the chance rate is 50% accuracy, the average classification accuracy for taste and texture under each condition is modest. We conducted a workshop with 2 sessions in a lab space to assess the accessibility of the FoodSkin workflow. We verified that all participants learned the FoodSkin techniques and completed the tasks within the allotted time. The results shows that users can adopt our design support system without any special training, but the manual fabrication process requires some proficiency training.